So after having seen concurrency control, we're going to see replication control in this next series of lectures. Today, in this lecture, we discuss replication. So what's the difference between concurrency control and replication control? Well, concurrency control deals with the case where you have multiple clients executing operations or transactions with just one server on the other hand. So you have multiple clients and one server on the other hand. Replication control focuses on the server side. Instead of having just one server, you have multiple server machines, and the objects are now spread out over these multiple server machines. You may have 5 objects which are stored, say 2 objects at one machine and 3 objects at another server, or you may have these objects replicated. So each of these objects has, say, 2 replicas at each of those 2 servers. So we'll discuss both the cases with and without replication in this series of lectures. So why is replication important at all? Well, first of all, replication means that an object has identical copies, each maintained by a separate server. These copies are typically called as replicas. I may use the term replica to also refer to not just the object copy itself, but also the server itself. So if I say the replica server, I mean the server that is storing a replica of the object. So why is replication important? Why is it important to have multiple identical copies of the same object? Well, there are a couple of reasons. The first reason is fault tolerance. If you maintain k replicas of each object, you can tolerate up to k-1 failures of any of the servers in the system. So if every object is replicated, say k equals 5 times, then your system, no matter how large it is, can tolerate up to 4 k-1 failures of any of the servers and still not lose any of these objects and still be able to serve out reads and writes to at least one of the copies of the objects. The second reason to do replication is load balancing. Essentially, if you have twice as many copies of a given object, then each of the copies faces only half the number of reads and writes that it does. So increasing the number of copies lowers the load on each of the copies by a factor of k if you have k replicas compared to just one replica. In general, the fault tolerance requirement can be captured as a higher availability requirement. So let's calculate what availability really is. So if any server, say all the servers are identical, just for the purposes of this discussion. So if each server is down a fraction f of the time, f might be, some small number like 5% or 0.05. That's the server's failure probability. So if you don't have any replication where each object is stored on exactly one server, then the probability that the object is available is the probability that the server is up, which is just 1 minus the server's failure probability, or 1 minus f. Okay. So when you have k replicas, the availability of the object is the probability that at least one of the k replica servers is up, which is 1 minus the probability that all the replica servers are down. And that second probability, the probability that all the replica servers are down, is simply the failure probability of one server raised to the number of servers, or f to the power k. So that's 1 minus f power k. Okay, so for those of you who know your math and probability, you will notice that as k is higher, this number at 1 minus f power k is actually much closer to 1 than 1 minus f. How close is it? Well, let's look at some real numbers. So here is a table that shows you in the first column the failure probability f. So we have several sample values, 0.1, 0.05, 0.01. These are the failure probabilities of a single server. And then in the next column, it shows what is the availability of the object when you have no replication, where exactly one copy of the object is maintained. Essentially, this value is just 1 minus f. So 1 minus 0.1 is 0.9, which is 90%, and 1 minus 0.05 is 0.95, which is 95%, and so on and so forth. With k equals 3 replicas, you can calculate the availability of the object as 1 minus f power k, and that turns out, for f equals 0.1, it turns out to be 99.9%. This is often called as 3 nines of reliability, because you have 3 nines over here, 99.9%. With f equals 0.05, the availability goes up because the server failure probability has gone down, so it's gone up to 99.9875%. When you have f equals 0.01, you actually end up having 6 nines of reliability, 99.9999%. So that's a much higher reliability. And now, when you see nines of reliability being offered in an industry product or an industry service, now you know what exactly it means. They're actually talking about the availability percentages as we're talking about here. With a higher number of replicas, you get a much higher availability. So just compare, when you have f equals 0.1, when you have k equals 3 replicas, you have 3 nines of reliability. But when you have k equals 5 replicas, you have 5 nines of reliability. Similarly, with failure probability of f equals 0.01, with no replication, you have 2 nines of reliability. With k equals 3 replicas, you have 6 nines of reliability. And with k equals 5 replicas, you have 10 nines of reliability. You can actually tune the number of replicas you have based on the failure probability that you expect to get the desired reliability from your system. So what's the catch? All this seems great, right? I mean, replication seems to give a lot of benefits. So what is the hard part? Well, the hard part is to guarantee two properties: replication transparency and replication consistency. Replication transparency essentially says that a client, any client, should not be able to see that there are multiple copies or multiple replicas of a given object. So as far as the client is concerned, the replication should be invisible or transparent. That is, the client should be able to execute operations just like there is just one copy of each object on the server side. The second, replication consistency, is similar, but it's slightly different. Here it talks about multiple clients seeing a consistent copy of the data in spite of replication. So in spite of the fact that the object is replicated, you want multiple clients to always perform operations as if there is only one copy of the data. And whenever a client updates or writes that the object, any replica of the object, all the other replicas get updated, if possible, instantly. And if not instantly, at least as quickly as possible, so that before the next client performs its operation, all the replicas are up to date. Replication consistency means something stronger when you have transactions. Essentially, it means that you guarantee the ACID properties, which is atomicity, consistency, isolation, and durability, that you have seen earlier in our discussion on concurrency control. So how do you provide replication transparency? Well, typically you provide it using front end. So you have multiple clients. Think of these as, for instance, the clients accessing a flight reservation database. The replicas are storing information about the objects, such as the flights, and you have a few front-end servers. These might be front-end servers maintained at the data center, or there might be front-end servers maintained at a content distribution network, CDN, or some series of proxy servers or cache servers. Essentially, the clients only talk to the front end, so they don't see any replica groups or any replicas of the objects, and the front ends are then responsible for forwarding the requests to the corresponding replica objects. Here I have an object O that has 3 replicas marked as replica 1, replica 2, and replica 3. Whenever a front end receives a request from a client, it then forwards the request to the replica, and the replies come back from the replica group to the front end and then back to the client along the reverse path. Well, what about replication consistency? Well, there's two flavors to providing replication consistency. They are known as passive replication and active replication. In passive replication, we use a primary replica, also known as a master or a leader. In active replication, there is no leader. Instead, we use a fully distributed approach among the replicas. We'll discuss each of these approaches in the next few slides, but both these approaches use the concept of replicated state machine. Well, a state machine, some of you might know, is essentially a program or a series or a code which, when given a series of inputs, gives a series of outputs, but for each input, the internal state of the state machine might change as well. So essentially, typically you have a graph involving states and transition rules in between pairs of states, and whenever you receive an input, you have an output, but you may also transition the state machine from one state to another. Essentially, replicated state machine says that all the replicas of the given object are running the same state machine or the same code. And when they are given an identical series or an identical sequence of inputs at each of those replicated state machines, the series of states that those state machines go through is identical. Also, the series of outputs is also identical. Fred Schneider in 1990 formalized this as follows. He said that replicated state machines refer to multiple copies of the same state machine begun in the start state and receiving the same inputs in the same order will arrive at the same state, final state, having generated the same series of outputs. Okay, so that's essentially a replicated state machine. So now let's look at passive replication and active replication. So in passive replication, the group of replicas of object O elects one of the replicas as a master or a leader, and for this it uses one of our leader election protocols that you have seen earlier in the course. the front ends, whenever they receive a read or a write, they relay the operation directly to the master. And this ensures that for writes, there is a total ordering of all the writes or of all the updates. For reads, some variants of passive replication allow the front ends to contact any of the three replicas for the reads, and some other flavors of passive replication direct the reads as well through the master. As far as writes are concerned, they need to go through the master, because the master then sends out the corresponding writes to the other replicas inside the group. What happens when the master fails? Well, when the master fails, you again run your leader election protocol, whatever is your favorite leader election protocol, and you elect a new master. In comparison to passive replication, active replication does not use a master or a leader. Instead, each of the front ends multicasts out the request, read or write, to the entire replica group. Okay, so for this, you can use your own favorite multicast protocol that you've seen earlier in the course. So the red arrows over here show a multicast inside the replica group. Now, as you know, multicasts come in different flavors, especially ordering flavors. So you can use any flavor of multicast ordering depending on the application. And as you've seen earlier in the course, the flavors of ordering that are available to you are FIFO ordering, causal ordering, total ordering, or in fact even hybrid ordering among these two, among these three. So if you use a total or hybrid ordering with total, so some form of total ordering, along with the replicated state machines, essentially it means that all the replicas are going to receive the same series of operations in the same order. And that means the series of states that they transition through and the series of outputs that they will output will all be identical at all the replicas. They may not happen at the same instant of physical time at all the replicas, but at least the ordering is the same. So what about failures? How do you incorporate failures into this multicast? Once again, as we have seen before in our discussion of multicast, you can use the concept or abstraction known as virtual synchrony or view synchrony, which orders failures along with multicasts within the group. So if you use virtual synchrony with total ordering for multicasts, essentially all the replicas see all the membership changes, failures, joins, or leaves, in the same order, and also the multicasts in the same order, and both of them, multicast and the membership changes, in the same order. Now you can use total ordering here if your application is okay with a slightly weaker form of ordering, which is causal ordering. That might be fine too. You could use that too, or even FIFO ordering if your application is willing to live with that. What do you do with transactions when you have replicated systems? Well, there is this concept known as one-copy serializability. Just like we studied serial equivalence for transactions when we studied concurrency control, in replication control for transactions, there is a concept known as one-copy serializability. What does it say? It says the following: a concurrent execution of transactions in a replicated database is one-copy serializable. So when I say concurrent execution of transactions, I'm talking about multiple clients executing transactions. Replicated database means that objects have multiple replicas on the server side. So it's one copy serializable if it is equivalent to a serial execution. When I say serial, it means a serial equivalence, right? Execution of these transactions over a single logical copy of the database. Okay, so it's as if you executed these transactions one at a time over a database where there was exactly one copy of each object. Okay? In other words, this is saying that the effect of the transactions performed by the clients should be the same as if they had been performed one at a time on a single set of objects, that is one replica per object. Okay, so this essentially means serial equivalence of the transactions, right? So that's what we're talking about here. Okay, so we want to have both serial equivalence and one copy serializability, and one copy serializability appears to capture the serial equivalence notion as well. So after this, we'll discuss how do you commit transactions when you have distributed servers on the server side.